working day, so just to compensate that, it is being scheduled to Saturday, Sunday, right? So as usual, those who are seen me earlier, the way I used to present my content is through uh, the presentation. At the same time, I'll also use some hand notes where I can write and explain things just like a blackboard writing, right? And if you happen to have any clarification, anything in between, you please uh, send a chat message. So I will, on there itself, I'll just clarify. Okay. Okay. I think my voice is loud and clear to all of you. I think we can start now. Okay then. Yeah. Thank you. Thank you, Surendraji. Right. So as I was asked to talk about this quantum memories and what are the requirements to be satisfied to realize a quantum memories. That is what we will discuss today. Okay. And having known these requirements, okay, having satisfying these requirements, how are we going to implement? What I mean is, how are we going to realize quantum memories for a quantum computing tasks? Okay, fine. So let me go further. Okay, right. So here you see, we usually have classical memory background. Okay, we understand that what how it is being done, and based on that, we will try to build the new knowledge of quantum memory. Per se, for the time being, please assume yourself that you are not having any idea on what is quantum memory, and having the idea how classical memory is being realized and what it does. We will from there we will build. Okay, so I have here for you a chart where classical and quantum memory is being in a way compared from different context. Okay, you see here, first of all, what is classical memory from the perspective, okay, from the perspective, 1 minute, from the perspective information unit. Okay, so here you see, from the property or the perspective of information unit, classical memory is just a storage unit which can store bits 0 or 1. Okay, how it is being done we will see as we go through, even in the classical case, and from there we build on quantum case. Okay, so for sure classical bits is a binary information which is in the form of 0 or 1 we will store, and any information we wanted to store, let's say a word or some numbers, which can be easily encoded in terms of binary strings. So binary strings is consisting of zeros and ones. Those things are stored on a classical memory unit. Okay, so that is what classical memory is. But if I have to have a quantum memory, it is not as straightforward as 0 and 1. It is an interesting form of 0 and 1 together. That's a superposition for you. A quantum state, by now you are comfortable with the Dirac notation of a quantum state, which is having superposition of 0 and 1 kit, where alpha and betas are probability amplitudes. In the form of alpha and beta, I'm going to store the information of 2 bits, which is 0 and 1 together on a single quantum memory unit. So that is a qubit for us, a short form for quantum bit. Okay, fine. So that is the qubit for you. When it comes to information perspective, this is what classical memory and this is what the quantum memory is. Now, when it comes to nature of it, if you see what is a classical memory, it is a deterministic unit. What I mean is, let's say I have a classical memory, I store a bit 0 on that memory, it is going to remain 0 with the 100% probability. Means it is going to stay in the same 0 form unless somebody comes and changes or disturbs it. It is just like any classical object in a real world scenario. What I mean is, let's say I have some object which is I kept on the table. It's a classical object, it's a macroscopic object. It is going to stay there on the desk for as long as time if somebody comes and disturbs it. Okay, so that is a deterministic thing for me. So classical memory is something of that sort. Okay, when it comes to quantum memory, it is a superposition, by the way, and it is like the same memory is going to have 0 and 1 together in a probabilistic manner. It is similar to if I toss a coin during the flight. Okay, if I toss a coin during the flight, what I see, both head and tail flipping. During the flight time, if I see the coin, I see in a way both head and tail in a fuzzy manner. I see. So quantum memory is of that sort. Okay, right? Okay. If somebody is saying we missed, don't worry. I am summarizing whenever I need. Okay, you may recover it. So what are we doing right now? We are trying to understand the initial description of what is quantum memory from the build from the foundation of classical memory. Okay, so the classical memory is a binary information storage units like a zeros and ones, which is deterministic in nature, means it stays forever in the same form. When I start whichever form it start. Okay, but when it comes to quantum qubit or a quantum memory is, it is not going to stay. It may go flipping between 0 and 1 continuously. With what frequency it is flipping, with what probability it is flipping, that is the means for me to store the information. Okay, all right. So that is about the nature. Let's see now when it comes to reading it. Okay, so it's a very interesting difference between classical and quantum memory here. You see, when I have a classical memory is being stored somewhere, a memory location, I can read that location, the information, as many times I want if I am careful enough. Without destroying it, I can read it. Means I can retrieve the information is being stored on a quantum classical memory. So here it says it is a non-destructive measurement. Means I can, without losing the intact, so losing the essence or the nature of the classical memory, I can retrieve the information. Okay. Why I'm saying non-destructive? Because when it comes to quantum memory, if I try to read it, the measurement by nature, in the case of quantum physics or quantum mechanics, measurement destroys the nature of quantum state. Okay, it is just like use and throw material. I take the material, use it, and the next there is no further use, so I had to throw it off. So it is like a one time pad, one time use material or one time unit. So the measurement would destroy the state. And how it destroys? It collapses. It forces the quantumness to fall to classical form. In a way, if it is in a superposition state, a measurement may drop that state to one of the zero, uh, one kit. That is possible. Okay, so which means you have to be very much sure when you have to make a measurement on a quantum system. So just for cross checking, sometime we will just do a check and we'll say we'll check now, later we'll do the computation. It is not. So you have to make sure yourself sure about making a measurement, then we are going to get the information out of it. Okay, so there's a question here: what exactly makes the destroy during the measurement? A very good question. Okay, so let me use my hand notes here. Okay, right. So let's take a simple classical example. I will say not, I'll not say classical, I'll take a classical analog. Okay, so the classical analog, let me take. Okay, what I mean is, let's take a coin, a fair coin, which has head, which has tail. So if a coin is there, okay, right, a coin is there. On one side I have a head, on other side I have a tail. Let's say if I flip a coin, okay. So during the flight, if you notice, coin has a possibility to exist in both the forms, head and tail. Now, during the flight, okay, if I have to find what is the coin, first of all, if I toss the coin, if I somebody comes during the flight and they see, they may say that, yeah, of course it's a coin. It's what kind of a coin is? Is it a 5 rupee coin or a 2 rupee coin? If they want to know what is the coin is, they have to catch it. Okay. Once they catch it, what happens? The flight is being destroyed. The superposition is being destroyed. So there is no other go other than destroying the coin flipping state to find about the coin. So that is a classical analog, which would help us to understand why the destruction of a quantum state happens when I make a measurement. Okay, so this is a classical analog. When it comes to quantum, the real quantum, what is the state it would be? It is a superposition state. Okay, fine. It is a superposition state. By the way, what is this superposition state is all about? So when you go back and use semi-classical picture or a quantum picture, what is it is a quantum system of, let's say, an electron can exist in the ground state, which is very close to the nucleus, and it may stay away from the nucleus. An electron I'm talking about. Okay, so let's say initially the electron is in the ground state. Now when I supply a photon of electron of energy, exactly matches with the separation of this orbital state, this between these orbits, what happens? The electron may jump to the higher state. I'm saying electron is not certainly jumping. It may jump or may not jump. For sure, if I try the experiment for 100 times, let's say some 60, 70 times it will jump, it will stay there on the excited state. And it can't stay there forever. It will stay there for 1 microsecond. You see, after 1 microsecond, it drops down to the ground state again because it can't stay there, and it emits the whatever photon it has observed in the first place. Now, let's say it is about to drop down. Again, I will send one more photon, which is exactly 1 microsecond apart. So what happens? By the time electron comes down, one more next photon comes, puts the electron in the excited state. So what is happening is I'll place the sequence of photons if 1 microsecond apart. So it is just like a juggling something. If something comes into my hand, I just throw it up, throw it away continuously. It's like continuously what I see, electron is doing a hopping between ground and excited continuously. It's like at some time it may appear to me it is in the ground state. At some time it may appear to me in the excited state. Okay, so this is a superposition state. Now it's like a fan wing is rotating. When I switch on the fan, the wing appears to be everywhere. It's like when I toss a coin, I see both head and tail in a fuzzy manner. I see both head and tail in a fuzzy manner, which means coin is in the superposition state. Fan wing is in superposition states of various directions in 360 degrees. Okay, right? The same way, the superposition is there. Now how do I write the superposition like this? Okay, so here the way it is written is, when I make a measurement on the quantum state which is in superposition, sometimes I find it in 0, sometimes I find it in one state. What is this sometime? Which means I perform the experiment for 100 times. Or I'll take a same quantum states, superposition states of 100 of them I'll take. I'll make observations of all the 100 of them. Out of 100, some of them found in zero state with a probability, let's say 60%. Another 40 will be found in excited state. So that is the alpha and beta for me. According to that, I'll explain the in a using a probability mechanism or a probability concept, how a electron is being in both the quantum and excited state. That is a superposition for me. Okay. Now, whenever it is in that such of a superposition state, when I try to see what happens, what I am doing, seeing means what? I am sending a photon onto. Okay, for example, if there is a box, within the box, let's say there is a atom which is in superposition. Atom means its electron, outermost electron is in superposition between ground and excited state. Now, to know in which state the electron is inside the atom, what should I do? I should peek in. Means I have to make a hole somewhere and just look into it. When I say look into it, means I'm sending a photon. Another photon may go, it might disturb the same superposition state. It is minding its own business of being in superposition state. It is just like when I give a torque to a coin, a flip, so it is being in a superposition state continuously. Okay, so during that, if somebody comes and catching is like making a measurement, so another photon comes, just disturbs this flipping state and put the atom from the superposition state to one of the state, either 0 and 1. So that is what a measurement is all about. Okay, so somebody was asking, what is this measurement? A measurement is just sending another pulse of photon or another photon onto the system, which goes and hits this atom or the electron which is in superposition, disturbs it, and takes the information of that electron, comes out as a rebound. From there I measure what is the nature of the quantum state is. Okay, right? So I can understand in that form. Let me see, is there any other question? Okay, wait a minute. Yeah, why do we actually use quantum communication if it is so cumbersome? No, it's not cumbersome, right? So it's not a cumbersome. You might say it may be confusing, ambiguous, right? So whenever things are, let's say something is not something is not clear, like ambiguous, even that ambiguousness can be expressed in terms of probability, and that probability could be exploited to use it for our own advantage. That is what probability 60% and 40% in terms of alphas and beta is being used to do quantum computing. Okay, used to do some computational tasks in much faster way, in much effective way compared to classical communication. That's why we are getting into the quantum domain. It is providing an advantage of seeing all the possible solutions for a given problem in one go. In that way, I can pick. Okay, if I use a classical computing task, let's say a parallel computer or a supercomputer, probably it might only see few possible solutions, or it might do solutions may be found from each available section to next available section in a sequence manner, in a parallel manner. But when it comes to quantum computing, there is no need to do parallel manner. Everything is in one go. It sees everything in one go. It's like a god talks to everybody in one given time. In that way, it allows us to do the computing task. That's why it's more powerful than classical computing or a classical memory in this case. Okay, right? So there is few more questions. Let me answer quickly then. What is a superposition state? So essential. Superposition state is a probabilistic state. It's like a coin being tossed. That is the best classical analog which can be used to understand what is a quantum memory and what is superposition state. Superposition state mathematically very very simple thing. Okay, right? If you just take a two-dimensional Cartesian coordinate system, let's say there is a I cap and j cap are a x-axis and y axis. Let's say somebody is there at some point on a surface. What do you do? If I have to specify where is this guy is standing with respect to some reference point, let's say what you do, you draw a position vector to that point and you just give a position vector r. What is this position vector r? R is xi plus yj. What you are saying is this position of this person along the x-axis is displayed by x value, along the y-axis is displayed by y value, y component value. Okay, y coordinate. So we are going to use the superposition to express where is this guy deviated from the origin in a two-dimensional fashion. If he's moving on a one dimension, we simply give it one variable, but this guy is moving on a two dimension. That's why I use a superposition. Similarly, quantum state is a superposition of something. It has two dimensions. What are those two dimensions? One dimension may be along the zero, another dimension is along the one, right? It's just like what you see. Classical Cartesian coordinate system is made up of I and j basis vectors. Okay. Similarly, a quantum system is made up of zero ket and one ket bases. You see? So this is called a vector space constructed, which is named after Hilbert space. Okay, right? So the other one, the classical analog, which is just a simple vector space, a two-dimensional vector space where any point would be described by unit vectors I and j cap. Okay, right? So that is the superposition state. Why it is so essential? It is essential to store multiple informations in one quantum unit. So when I say qubit, which allows me to store 2 bits of information, when I take a two qubits together, let's say there is a qubit 1, I will call it qubit A, so which can be alpha A 0 ket, alpha beta A 1 ket. Another qubit is, let's say, B, alpha B 0 ket, beta B 1 ket. So these are the two atoms I have. Both are in superposition. What I'll do, I'll just put them together. When I put it into one box, let's say atom A and atom B I take. When I make them interact, what happens? They may just interact and exchange the information, their superposition, their probabilities. What happens when they're about to interact? I can just show the quantum states could be a simply tensor product of individual quantum states. Here, what do I be getting is alpha A, alpha B, 0, 0 plus alpha A, beta B, 0, 1 plus, okay, okay, alpha B, 1 minute, alpha B, okay, alpha B, beta A, 1, 0, sorry, 0, 1, 0, 1, yeah, something like that. And beta B, uh, sorry, beta beta A, beta B. This is 1, 1. 0 0 0 1 1 0 1 1. Okay, you see now I have a new basis defined as 0 1 1 0 1 1. This is a new basis. It's a 4-bit basis. Okay, so this is how a higher dimension is being constructed by bringing two symbol qubit systems. Okay, I can go on expand the dimensions as much as I want. How? I just take two atoms or two qubits gives me 4-bit space. If I take 2 to the power of n, I'll get a huge bit space. Okay, so 2 to the power of n is very large. Okay, right? So if I go for 2 to the power of 150 or 2 to the power of 500 and so on, I can expand the data space, and in a way to study this entire bit space in one go. I can study how I just take that overall compound system. I'll study that compound system. That is why the superposition state is very, very essential to do any computing. Okay, fine. So there is one more question here. How can you measure 100 times when after one measurement electron collapses? A very good question. Okay, it's very, very important. Fine. So that's why when I have a quantum state, alpha 0 plus beta 1. Okay, I just now I told when I make a measurement, it falls to one of the state. Very good. And how can I say 100% or how many 100 times? Okay, let me tell you. I can take such like atoms, 100 of them, and make a measurement in one go, right? Okay, 100 of them in one go, and out of which I'll get the probability. What is the state of falling into one, let's say zero state, and what is the probability of falling into one? I'll do that. Let me ask you later in the presentation. I'm going to say no cloning is possible in the case of quantum computing, and you can give a counter question to me again. How can you make 100 such like atoms when you are not able to make a replication or a cloning? Okay, let me tell you, when I have a coin, let's say classical coin, even it's a micro object, microscopic object, when I ask you if the coin is given to you, what is the chance of your when I tossed, what is the chance of finding a heads when I catch it? If I ask, you would simply give it's a fine coin. Obviously, it is a 50% chance. It doesn't mean I made an experiment of 100 times and out of 100 I got it. But by default, it's a fair coin. Similarly, when I make a qubit, in that way I will make it. In such a way, when I make a measurement on such qubits, like 100 of such thing, how many times it falls to zero, how many times it falls to one, that is how I'll do. Okay, how do I choose? Based on my preparation itself, I just gave you how do I prepare a superposition state. This is what I take my qubits, sorry, my photons equally spaced, 1 microsecond equally spaced. Whatever I'll be getting, I'll be getting 50% chance qubit falling in zero, 50% chance in falling in one. Okay, and I just take a sequence of such photons. If I put them together in mathematically, those photons would constitute something called a pi by 2 pulse or a pi pulse. It's called pi pulse. So what is this pi? The area under the curve, if you find out using some complex analysis, it is comes out to be the pi radians or a pi by 2 radians. Okay, so this is the area under the curve, which is actually a pulse sequence. I can increase the area of the pulse or decrease the area of the pulse. In that way, I can fiddle with alpha and beta values, how much alpha and beta values I should have. In that way, I control my superposition of my coin. Okay, it is just like I have a coin, I stick something on head side, let's say some weight I stick, let's say some small magnet I stick to one of the side, and if I toss the coin, the other side comes on the top more because there is a biasing done for the head side. So the way I'm biasing my coin is something in the case of quantum computing, preparing my pulse to create a superposition. Okay, right? Okay, I hope I cleared that question. Just for intuition understanding, I'm telling I perform the experiment 100 times. From there, I get what is the chance of finding in zero state, what is the chance of finding in one state. At the same time, the same experiment also can be understood as 100 of that same experiments were done by 100 people, 100 people reporting the answer. From there, I make what is my alpha and beta. Okay, just for intuition, it is being said. Okay, now, just a minute. 1 minute. I just shut down my mobile. Ah, thank you. Okay, so there is one more question here. One general question. The memory related subject should be in quantum computing, but we are getting to learn in quantum communication series. Does it has a role for performing secured communication? Please do not mind, sir, for asking this question. Very good. So let me tell you. See, quantum memory is not confined to any particular subject. Okay, first of all, when I'm doing a computing means what? I am taking a quantum bit storage, many bit storages, and fiddling with them or processing them. So the quantum memory is a fundamental unit on which everything else is built. Only thing when it comes to computing, you may not be bothering about how the memory is being realized at the hardware level. So you take it for granted that I have a information is being stored as some superposition state. When it comes to hardware realization, how it is being done is a memory. Okay, so there is no harm in getting to know how the memory is being realized. So when it comes to CSC, the computer science engineering, whether you are doing a software or hardware, it is all about the storage unit. When it comes to software, the software engineers may not bother how the actual hard disk works, how the SSD works. They don't care. So they start to program it, and they assume that they are programming from the information is being fed to the system on their own terms, but it is converted to binary form, and then information is processed at the processor level and then converted back to regular conventional information, which is spit out at the monitor, or let's say some information out by the computer. Okay, so please don't bother. Quantum communication do deals with quantum memory, and quantum computing also deals with quantum memory. When it comes to communication, I'm sorry, when it comes to communication, why it is so important is, okay, communication means quantum bits being communicated from one point to other point, like quantum qubits are transferred. So I need a way to transfer the information. So I need a way to store the information at one point. So the information is stored at one point, let's say a node, a storage node. Okay, so there I have a okay, stationary qubits, which could be a single atoms or a single electrons being in superposition state. When I have to send that superposition information elsewhere, what I do, somehow I have to convert the information of the stationary state into a dynamic, a flowing qubit state. Okay, so that is a dynamic qubit. Okay, which is a photon, by the way. So the photon carries the information of that qubit, and which travels along the, let's say, optical fiber and goes to another node. There, let's say there is an electron which is the ground state, which can be put into superposition state as the photon comes and interacts. Okay, so it may not be one single photon, it's maybe a stream of photons carrying the information of the initial stationary state. Okay, so that's why the photons are called flying qubits, and electrons in a superposition state are called the stationary qubits. Okay, so in the case of communication, we are dealing with a memory node, and we are dealing with the receiving node, and along the way a quantum memory or a quantum qubit is traveling in the form of photon. So that's why we need to understand a quantum memory here in the communication. Okay. Okay, so in the tomorrow session we will also see why I need to do some kind of a repeating thing, quantum entanglement based, some kind of a measurement task I have to do in between these two nodes, node sender and node receiver. Okay, to ensure that information is traveling without any decay, because when I send the information along the way, it can't travel for a longer distance. Obviously it will get reduces its intensity, because as it travels it reduces the energy, gets consumes the energy. So to avoid, okay, to avoid such a decay of the information, I have to do a amplification. But in the case of quantum computing, I don't have a kind of a amplification kind of a task. So there I need to do something else. It's called a quantum repeater or entanglement swapping, or it is also called Bell state measurement, that we will see tomorrow. Okay, so that is why quantum memories are very, very important in the case of communication. Having said that, it is also going to be important in the case of computing. Okay, yeah. Okay, another other qubits will be in many states. What is it? Sorry, qubits are very good, very good. Okay, so right, so qubits are something which are in superposition of 0 and 1. Okay, so qubit means it is in bistable state. Okay, it is in the superposition state 0 or 1. Fine. And there is something called qubits. What you said is absolutely right. Qubit means a quantum system which exists in d states, where d can be any number. In the above case, in the qubit case, what is the d? D is just 2. Okay, so in qubit states, d can be anything. For example, if d is 3, what is d is 3? I have 3 states: 0, 1 and 2. Okay, so now let's say electron is there. It can exist in 0 state, or it can exist in 1 state, or it exists in 2 states. Probably it might go to 1 and come back, or it may go to 2 and come back, and anywhere at a given point it can exist. It is just like its presence is being stored across, shared across 0 and 1 and 2. So I would say there is a probability amplitude corresponding to 0, there is a probability amplitude corresponding to 1, there is a probability amplitude corresponding to 2. So what is the exact probability? Exact probability is p0 is alpha 0 absolute square, p1 is alpha 1 absolute square, p2 is alpha 2 absolute square. So whenever I say qubit with a d equal to 3 state, it is called a qubit. Okay, I can go quadrat, 4 states. Apart from 0, 1, 2, I can have 3 more and 1 more. 0, 1, 2, and 3. Okay, so if I just take a naturally available atom, if there is only one free electron, let's say that it's in the initial state is, let's make call it a 0, and all above that state it can go and exist in any state. So there are 4 state quadrat. Okay, I can keep on increasing the d values, the dimension values, for a larger values. But the question is, with a single atom, if I try to realize 3 state qubit system, okay, there is a chance if I try to create a information processing at any 2 levels, only there is a chance that it might spill over to somewhere else. So that's why the q treats are not preferred compared to qubit. Let's say I have to realize a higher dimensional quantum system. What do? Earlier I just said, here you see, I just take 2 atoms together, I realize a 4-bit system. You can say a quadrat, just like a q trait. So this time dimension is 4, d is 4. If I take one more atom additionally, I'll get octet. Means d equal to 8 if I with a n equal to 3 qubits. Because 2 to the power of 3 is 8. So I can have qubit with the d equal to 8, 8-bit system or 8-base system. That is what qubits are. Okay, right? Okay, then few more questions I'll clarify. Okay, quantum communication is more effective because you can express whole lot of ambiguous states than few determinate states expressed by classical communication. You are right, Monisha ji, absolutely. So at a time, in a one go, I can store all the information on one quantum superposition state that can be transported or transformed to one location to other location. In that way, I can send, and at the same time I can process that in one go. It's not like I will process bit by bit or a point by point and a superposition. It's not like that. At a time I can process. That is a possibility of quantum communication. Okay, right. So Chandrasekhar ji is asking, sir, how can we take the state of a coin during the flight? It is not stable state. How data is stored in that state for general science? A very good question. So please note down. I just said A toss of a coin is not equivalent to quantum qubit. I'm not saying that. Toss of a coin is a classical analog which could be used to understand what is the superposition state when it comes to quantum qubit, quantum superposition state. Okay. Yes, I agree. It's in a dynamical form. It means continuously changing. It is continuously changing. It is not stationary. It is not stable. But it is carrying the information of probabilities on it. You see, what are the probabilities? When I catch the coin, let's say once I get head, it doesn't mean 100% of the time I find head. It's not that. So again and again I have to toss the coin and catch it. Out of 100 times I find it 50 times head, 50 times tail. What it means, it's a fair coin having a 50% probability to come in ground head state, 50% probability to come in tail state. That is what the coin toss is conveying to us. Similarly, when I take a quantum superposition state which is oscillating between ground and excited state, it is a dynamical state. It is not a stable state. It exists. Such superposition exists only for few seconds. That is called a coherence time. We will see. It may appear in that superposition state for 1 minute or sometime few minutes. So within that time, we can do a lot of things. We can process the information using the gates. Okay, right? So using the gates, I can process the information. I can do a simple task like adding two numbers. Let's say full adder, half adder is there in classical computing. In the same way, I can use these probabilities being stored as a superposition probability amplitudes, which can be processed. And using that processing, I can do a computation that is enough for me to do a lot of things. Okay. So that is what even the ambiguous or even confusing, even dynamic, even indeterministic superposition things allows me to do a constructive things. Okay, right? Okay, so there is a final question. When we say probabilistic, can we obtain specific superposition state? We are actually dealing with specific superposition states only. Inside a specific superposition state, you see, inside a superposition state, okay, it is a specific superposition exactly corresponding to this state. There is a fixed alpha, fixed beta, that is very specific. Okay, only thing is that values alpha absolute square plus beta absolute square is going to be 1. It's the probabilities, it's some going to 1. So that's why it is specific, but it is a number runs between 0 to 1. Okay, right. Okay, so there is a one more question. You said measurement means second photon is sent and we get the ket 0 or 1. Once this is done, what happens to the photon? Very good, very good, very good. Okay, right, fine. So let me go a fresh paper. Let's say I have a qubit which is superposing, it's doing oscillations. Okay, fine. It is doing a coin. When I send a photon, some photon, so this electron is minding its own oscillating, like flicking between. Let's say what happens, this photon, which is, let's say the electron is, when it is about to come down, this photon go and hits it and puts back. And in that way, it is disturbing its nature. Okay. It is just like a swing. Let's say somebody is swinging in let's say somebody is swinging in a park. Okay, if you go on in resonance, if you hit the swing, it being in a swing, it swings continuously. But if you go on out of swing, like out of resonance, abruptly in opposite direction, if you just go and hit it, it stops abruptly. It is just like a fan is being rotating continuously. You go and take a stick and poke in between, it abruptly stops at that point. So that is what the measurement could be when it comes to quantum measurement. Okay, right? So it is like some photons were sent out of sync, and those photons will retrieve the information and come out, so they destroy it. Okay, so when it comes to mathematical representation, there is a very beautiful way I can express what is this measurement is all about. Okay, let's say a quantum state is represented on a basis of 0 and 1 basis, like that. So what is this basis? 0 and 1s, interestingly, are they are the basis elements, are the eigenvectors of z matrix. Okay, what is z matrix? Z matrix is, I'm sorry, z matrix is, okay, you know z matrix now, 1 0 0 minus 1. So which has got eigenvalues and eigenvectors. Z acting on 0 gives me 0. Z acting on 1 gives me minus of 1 ket. Okay, you can say minus of 1 ket. So 0 ket and 1 ket are the eigenvectors of Z. So I can make a measurement tools for the Z basis. See, this is a basis of Z. So I can make a measurement basis for Z using its eigenvectors. What is that? So which is outer product of 0 with 0, outer product of 1 with 1. These are the measurement operators. Okay, when I take this measurement operator, act on given superposition state, what happens? It pushes the quantum state to fall into one of the state. What is that? When I take mz0, okay, 1 minute, sorry, mz0, act on quantum state psychet. What is that? 0 alpha 0 plus beta 1. Okay, so this is like a measurement operation. So once I do measurement operation, what it happens? 0 ket alpha comes out, it takes the inner product with 0 with the 0, I'm sorry, 0 with the 0 plus 0 ket beta multiplied by 0 with 1. By the way, inner product with 1 is 1. Inner product of 0 with 1 is 0. So 0 multiplying to this entire thing is 0. So what is the result? mz0 acting on a given quantum state gives me what? Alpha 0 ket. Okay. With one measurement, I'll get a 0. Now I do several measurement and gets the what is the mean output. Okay, right? Okay, for example, if I'm I'm not sure about some patient's temperature, I have a thermometer. So sometimes thermometer works, sometimes doesn't work. What do? You do several measurements using the thermometer. You take the average of the all the measurements. Something of that sort. If I have to do average, what I do, something called, in the case of quantum state, it's called expectation value of given operator measurement. So what is that? It is quantum state multiplying on the either side to that measurement operator. So now on the right side measurement gives me that. What is the left side measurement? What is that? It is quantum state in the Bray form is, okay, alpha star 0 Bray, beta star 1 Bray, multiplying onto what is this? Alpha 0. By the way, inner product with this one and this one is 0. Inner product with this one is 1. So I'll be getting alpha star alpha, which is absolute alpha square. So I'm getting, when I make a measurement of operator mz0 onto a quantum state, I'll get the probability. And what is the state output? State output is this one. Okay, so quantum resulting output, if somebody asks me what is the resultant output when I make a measurement, which is simply a measurement operator divided by, okay, the quantum state scaled version. This is the output. Okay, right? Fine. So this is a resulting thing. Okay, so mathematically, this is what explains the measurement. When it comes to the reality experiments is, if something is oscillating, somebody is going to catch it abruptly, like a coin is being tossed or a fan is being rotating. That is what exactly happens in the case of measurements. Okay, right. I'll come to the questions down the line. Okay, so there is a question here. Yeah. Is it useful to have a good knowledge in quantum mechanics and quantum electronics to understand quantum technology? I would say whatever people are going through this QT-01 to QT-06 and 7 and so on, this is enough. You maybe whatever knowledge you are getting, this is enough to understand the quantum technology. Okay, right. There is a question on MZ. What is this MZ? Unadjusted state. Okay, please remember. Right, suppose if I want to represent any point on a two-dimensional space, okay, I'll take a superposition vector R, which is xi plus yj. Okay, it's a Cartesian coordinate system. I and j are Cartesian coordinate systems. Using that, any point on two-dimensional surface I can measure and represent. But the question is, let's say some body, some point P, not moving in straight lines, if it is going in a curved manner, using Cartesian coordinate system becomes not at all suitable. I need to use curvilinear coordinates or a polar coordinate system. What is this polar coordinate system? It is made up of r cap and theta cap on a two-dimensional polar coordinate system. What is that? R changes along the radial direction and theta changes perpendicular to that. R cap and theta cap. So theta changes like this. Okay. So polar coordinate system is used when things moves in a curved manner. So depending on the situation, I choose my base which I use to measure, which I use to represent. Okay. So similarly, whether the quantum system is based on alpha 0 plus beta 1 means it is constructed on 0 and 1. Okay, sometimes the same quantum state, it's like a 2-bit state, a bistable state, right? It can also be represented in some other form. What is that some other form? It can be a plus plus b minus. What is this plus? Plus is 0 plus 1 divided by square root of 2, minus is 0 minus 1 divided by square root of 2. This is also bistable state. Here also I have a basis. What is that? Plus gate and minus gate is another basis. Just like, see here two bases we have seen. Okay, just like I cap and j cap is a Cartesian polar coordinate system. This is, sorry, Cartesian coordinate system. This is a polar coordinate system. Okay, so depending on the system dynamics, I choose the right one to measure them. Okay, now the question is whether the given representation is in the form of 0 or 1 or a plus gate or minus gate. I don't know how to find it. Very simple. So if a patient is having a fever or not, how do? I take a thermometer and bring near to the patient and take the heat out of the patient and transfer to the thermometer, and how the this mercury of the thermometer expands. According to that, I'll find out. You see, so I use a tool which is based on the temperature to measure the temperature of a person. Same story, whether the quantum state is prepared out of 0 and 1 basis, or whether it is prepared on a plus gate or a minus gate basis, or I am going to create basis tools, measurement tools out of same basis tools. What are they? Okay, for example, 0 ket and 1 ket are the eigenvectors. They are the eigenvectors, okay, of Z matrix. What is Z matrix? Just now I told you. Z is 1 0 0 minus 1, and it has eigenvalues 0, eigenvectors 0 and 1. Okay, which means its a corresponding eigenvalues are plus 1 and minus 1. Eigenvectors are 0 ket and 1 ket. And whether the given state is constructed using the basis elements of 0 and 1, how do I know? I know to create a measurement tool like a thermometer based on the same temperature mechanism. What is that measurement tool is? I am going to construct a measurement tool MZ0 in an outer product form. Outer product 0 ket with multiplying a bray of 0, which is going to a matrix. What is that matrix? 1 0 0 0. How? Very simple. What is a 0 ket? 0 ket is 0 ket is 1 minute. 0 ket is 1 0. What is the 0 break? 1 0. So what is this? This is a 2 by 1. This is a 1 by 2. I am going to get a 2 by 2 matrix, which is 1 0 0 0. Okay. Similarly, what is mz1, which is outer product of 1 with 1? So which is going to be 0 0 0 1. Right? If you add both of them, interestingly, you see, it is going to give you identity matrix. So it is called completeness relation. Okay. So you see, measurement tools for me to find a given state is existing in 0 or 1. I'll construct using a same basis elements, which is called a measurement tools, mz0, mz1. So in a circuit it will be represented with a such a thing like a meter tool. Okay. Similarly, if the quantum state is constructed as plus state or a minus state, I need to find out what is this plus state and minus states are. Interestingly, if you find x acting on a plus state, going to give you 1 into plus state. X acting on a minus state give you 1 into minus state. So which means x gate, which is, what is x gate? X gate is 0 1 1 0, is having plus gate and minus gate as eigenvectors, and corresponding eigenvalues are plus minus 1, just like z. Only thing is eigenvectors are different. So what I do, I just create a measurement tool for plus gate as outer product of plus with a plus. Measurement tool for minus gate is my outer product of minus with a minus. Okay. So by the way, what do I get here? What do I get? What is the corresponding mx plus? What it will be? It will be 1 by square root of 2, 1 into 1, 1 by square root of 2, 1 into 1. So what do you get? 1 by 2, 1, 1, 1, 1. Sorry. Yeah. Right? Okay. So what about mx minus, which is mx minus is, okay, 1 by square root of 2, 1 minus 1 multiplied by, okay, 1 by 2, 1 minus 1, 1 by 2, 1 by square root of 2, 1 by square root, which is going to give me 1 by 2, 1 minus 1, okay, yeah, minus 1, 1. So this is the mx minus for you. Okay. So this measurement tools mz 0 comma 1 or mx plus or minus 1, these are the measurement tools would help me to find out my given quantum state is made up of 0 ket or 1 ket, or it is made up of plus ket or minus ket. So those are the measurement tools for me. That is what we see. So in a circuit, in a quantum circuit, they represent like this. So interestingly, let me tell you one more thing. 0 ket to 1 ket are called measurement basis. Measurement basis. Or it even called computational basis. I'm sorry. It's called computational. Most of the times it is being used. Okay. Plus ket and minus ket is slightly complicated or not complicated. It may have some other advantages. That's why it is being used. Okay. Right. Okay. I hope you got it. So these are the measurement tools. You can just think in a form of classical analogies. MZ0 and 1 are like a thermometers which allow me to represent, find the temperature of a person. MX plus or minus is like a pressure. Like you say, I want to find the pressure, blood pressure of somebody. So I use that measurement tool. Not thermometer. Thermometer not gives me a pressure of a person. Okay, right. So thank you very much. So we are too much deviating. It's fine. So better to clarify doubts here. Okay, there is a one question here. Okay, wait a minute. What are the key differences between terrestrial, satellite, and aerial quantum communication links in terms of signal loss and noise? And Professor Vardarajan sir is asking from SVU. Thank you for a broader question here. Okay, terrestrial, satellite, and aerial quantum communication. So when it comes to communication, as of now, more or less we are talking about the channel based communication, quantum channel based communication, where a quantum channel is being established for example, through an optical fiber. Okay, quantum. So there is a medium. So qubits were sent along and qubits were received at some point and will be assessed. Our qubit encoding is done, information encoding done at the sender, and it is being received at the receiver, and retrieve information is done. So more or less 60-70% of the time we are talking about, the information is being sent through a quantum channel. So you might say we are still at the medium communication, uh, uh, say a dedicated quantum channel communication we are considering. Now, right now, for the past 5 to 6 years, people are thinking, even exploring the possibility of sending the qubits in the form of some laser pulses from one node to other in a free space, in a surrounding, let's say, in a atmospheric weather conditions. This can be sent because they're they're powerful enough to travel without being disturbed by atmosphere. Okay, right? So the free space communication is being also explored. When it comes to the satellite or aerial future advanced level technology, of course, the target for us when it comes to aerial or a free space communication is, there are stationary like earth satellites at the orbit of the earth orbit. So there are satellites we want to communicate from the ground, okay, to the satellite. Okay, so the node which is sends, and satellites help us to communicate the nearby the receivers. So in that way, the communication is done without being compromised between the central node and the receiver nodes. Okay, so since directly communicating is not possible, may do it through aerial satellite communication. So this is being explored. It is at very early stage, I would say infant stage, mainly because the as of now the technology whatever we are at, so the whatever photons were sent with the quantumness intact in them, they are actually getting disturbed by the noise in the weather. Okay, so then due to that, people are exploring how can we overcome such noise impacts due to the weather conditions. In that way, we can just once we overcome, we can do a better communication. So this was a situation back then, before the radio communication. So things got, later on we were able to overcome, and then we are right now, we are actually doing, even there is a very good internet stream even in the airplanes. Okay, this from the Elon Musk's company, right? The Starlink, we get a very good internet even in the flights. Okay, right? So the technology is being developed. So in future, there will be a quantum communication being done in a free space with much more accuracy, and at the same with high security. So when it comes to quantum computing, third person cannot tap in because it is becomes impossible, or like a third person's probability of finding what the information is can be reduced to very small values using quantum Q distribution. Okay, right? So that is what the broader answer for your broader question, Professor Varadarajan sir. Okay, right. Okay, so the questions are coming in. From where can I get the knowledge of forming unitary matrix for a standard gate on an arbitrary gate? Any textbook? Ah, very good question. Okay, so let me tell you answer to your question quickly. The textbook for you, or textbook for you is, please explore the Quantum Mechanics by Shankar. Okay, or Quantum Mechanics by Jet Li. Okay, these are very good books talking about unitary matrix and so on. When it comes to answer to your question, quickly I'll tell you. Please remember, what is a gate? Gate is what? It's a some processing unit which changes. What's a gate? A gate is, a quantum gate is, it takes some quantum state, sends some new quantum state. It does some operation. So, a evolution of a new quantum state is nothing but a unitary evolution. So, for that, they show unitary operator acting on the old quantum state. What is this unitary operator? Unitary operator is exponential minus I Hamiltonian t divided by h cat multiply onto h. What is this Hamiltonian? It's not Hadamard gate. Please remember. Let me put a calligraphic h. The Hamiltonian is going to capture all the information around the system, and also the information which is coming and interacting with this. Like say a pulse comes and interacts with a qubit or a quantum system which is in strict ground state and make it superposition state. Okay, which means, let's say Hadamard gate, you take Hadamard gate. What is the Hadamard gate? What is H? H is 1 by square root of 2, 1, 1, 1 minus 1. This is Hadamard gate, which acts on, let's say, quantum state 0, puts into superposition state. You see, my old quantum state is 0 cat. What is my new quantum state? New quantum state is plus cat state. So my Hadamard gate is like that. Means my unitary operation on quantum state gives me, okay, plus cat state. So what is the unitary operator? Unitary operator would be having some exponential minus I ht divided by h cross. Now for Hadamard gate, you have to find what is the corresponding Hamiltonian. Okay, question is, what is the Hamiltonian for a given gate? Here in this case, H gate, Hadamard gate. So for any quantum gate, there is a Hamiltonian. If you know the Hamiltonian, you can find the unitary operation. So unitary operation is but nothing but a gate. So any quantum state which is changing from one form to other form is a unitary operation, or it's a unit matrix operation onto that. So you need to find. Okay. So this the quantum mechanics. Okay, there is a book. Yeah, I think Nielsen and Chuang is another book which talks about what is this unitary evolution, how to get the unitary evolution, or how to get a Hamiltonian for a given gate. Okay, so if you understand, you would really appreciate. Okay, sometime I think I did cover this part as an initial module. If you want, like, you can write to me, I can share one notes for that. Okay, thank you. Okay then. Okay, let me go further. Okay, so I quickly give a break, I think 5 minutes, and then we'll come back to the presentation. Okay, yeah, let's take a break. Yeah, I'll definitely show my notes. Yeah, whatever I'm writing here, this also I'll share. At the same time, my presentation also I'll share. Don't worry. So we are only at a very early stage. I have to cover a lot of things. Yeah, I'll do it in next 1 hour. Yeah, welcome back, everyone. I think we should hurry. Hmm. Okay, that is Muhammad Shikji is asking. Thank you for the. Okay, thank you for your appreciation. Okay, so Prahlad, you were saying measurement. Your explanation I missed because of net problem. So I did explain again. I think so. Please, I think you can check the recording later on. Check recording is also available. So measurement is nothing but some kind of a measuring tool acts on a given quantum state to find out what it is made up of, what it's consisting of. Okay, so mathematically they are like some matrices, operators, which are constructed based on the basis elements. There's a plus and minus basis is there, and 0 and 1 basis is there. From them you can create a measurement tools, whether it's a z basis or x basis we can find. Okay, if we get an inconclusive result with any of this measurement, which means we are using a wrong measurement tool. It's simply saying to measure my weight, let's say I use a measuring tape, so it's very much absurd, right? Okay, so to measure my height, if I try to using weighing balance would give me some number, but it is not equivalent to my weight. Okay, the same story, whenever I get an inconclusive result, which means I might have used the wrong measuring tool. So when I get a conclusive result means I am getting the right measurement. Okay, fine. So that you can go through and understand again my explanation. Okay. Okay, so there is a question here. Physically, when measuring a qubit state, the expectation answer is corresponding to what quantity is, sir? The result state must have a probability 1. Yeah, you are right. See, when I toss a coin, when I catch it, for certainly I'll get a head or tail, right? One of them will definitely fall. It doesn't mean 100% of the time I'm getting one of them. Okay. Say, I see certainly heads, means there is a probability, 100% probability I got the head, right? For every one measurement. But thing it is not, the coin, I will not say the coin is 100% times it comes head. Why? What I mean by that is, if I toss a coin 100 times, 50 times I see head, 50 times I see tail. That is what head and tail is all about. Okay, right? So please see it from that prospect. Okay, right. Is this slide under primary application? Why quantum computer is not there? Okay, primary application. Why quantum computer is not there? Yeah, quantum computer is there. I don't know what is the question. I think we'll come back to that later. Okay, I'll quickly get onto the presentation. So we need to complete this. Okay. So when it comes to quantum memory, I hope now you will know many things about the quantum memory. Copying classical memory is perfectly possible. Perfect duplication is possible. Cloning is possible. And quantum memory cannot be cloned. If I have a qubit, I can't replicate many qubits of that sort. Why? There is a quantum there is a concept, something based on no cloning. Quantum qubit cannot be cloned or can't be replicated. Okay, right? So there is something called coherence time. See, any memory, if you take, it comes with its own lifetime, beyond which I can't do anything. It loses its lifetime. It's called coherence. When I say coherence, means it's like a syncing, like a synchronization. Let's say it's like a 10 people, 10 dancers dancing on a stage in the same fashion. Doesn't matter what's their height or raw height or like say their weight. If they in sync, it looks very appealing. Let us somebody is going out of sync, we'll say it's not at all sync. Same thing, if I take a few qubits, all of them are behaving in the same fashion. That's what they call it. They are happen to be in a coherence. But they go out of coherence means I may not able to do the computation in a much effective manner. Okay. So the coherence time, the lifetime for a memory, classical memory is infinite or indefinite. Okay. It is being dictated by the power. How much power I can continuously I can send, that much time I can have a coherence time. But when it comes to classic quantum memory, I can't have a memory forever. So it is a lifetime of some number, starting from few microseconds to few seconds or even few minutes, coherence time based qubits being realized. Okay. So when it comes to classical memory, they are very robust to the noise outside environment, but quantum memories are extremely sensitive. They immediately become decoher with the noise coming in from the environment. So that's why we need to seal them in a very huge cylinders and pour them a lot of temperature, like a cooling liquid, to avoid the external ambient temperature coming in and disturbing the quantum qubits. That is where cryogenics is coming into the play when it comes to quantum computer. Okay, right? So there are qubits being realized at a room temperature, for example, photonic qubits. They can work at a room temperature. They are much robust to an external environment temperature. Okay, right. So primary applications you see here, data storage and computing is done when it comes to classical computing. When it comes to, yeah, I think Lakshmanaran Sinergy asking, in this application, primary application, quantum communication and quantum repeaters is being said, why there is no computing? Yes, there is a computing. Since the talk is about the next follow-up sessions is about communication, that's why I had put only these two things. Yes, please mind my uh, overlook. Okay, sorry, please excuse my overlook. So it is quantum computing is also there as a primary application. Okay, right. Thank you. Fine. So the examples are RAM, okay, solid state hard disk and high definition disks. When it comes to classical memory, when it comes to quantum memory, how it is being realized is, we can take few atoms, it's called atomic ensembles. I can take a NV centers, there is something called nitrogen vacancy centers inside a diamond. I can take few atoms and make them ions. I can trap the ions which are charged within certain location using electromagnetic fields. I can trap them and put them in superposition state, probably based spatial superposition or temporal superposition. Some kind of a superposition I can create when it comes to trapped ions. From there, I can realize a qubits or a quantum memories, and that I will be using for computational tasks. Okay. So can you please throw some light on quantum repeaters? Yeah, of course, tomorrow it will be discussed. Please uh, wait for tomorrow's session. Okay. Quantum repeaters are something which are based on Bell state measurements. Okay. They are the ones which are allows us to extend the quantum entanglement for a longer distance. Okay. And also, which is some kind of it's not an amplifier, it's some kind of a unit which allows me to extend my communication channel for a longer distance, because amplifying is not possible in a quantum computation. Okay, fine. So fine, so we know classical memory, how it is being realized. Let's recollect how classical memory works. Okay, it's like a two bistable, it's like a bistable physical system is there. It can exist in two state, just like a switch can be in 0 or 1, like a high or low. Okay, a transistor can be communicate like a transistor may allow current to flow through, or it may abruptly stop. It's like acts like a like a switch on off mode. Okay, so if any unit has possibility of existing two possible states at different times, okay, in different mode, it's like a classical memory for me. Okay, so one simple example is given here. There may be a system with an energy barrier in between two states. Okay, they both can be a low state, but they are two different low states. Okay, what I mean is, these low states are low enough, they should not be disturbed by the room temperature. Such states we can choose and realize some kind of a switch effect. From there, I can do a memory storage. For example, I want to store a 0, I can put the state in red. If I want to store 1, I put the state in green state. Okay, so that is how it is being done. When it comes to, 1 minute, actual realization, here I have here memory realizations. Okay, so I can put the system in a high voltage state, or I can put the system in low voltage state, a transistor. Okay, so at some exiting point, there are three nodes for a transistor. One of the node I can dictate based on the other two node voltage difference or a current through other two nodes in the transistor. The third node power output or a power voltage can be controlled between high and old, high and low. In that way, I can have something called classical memory. Okay, so that is electronic memory. Okay, right? And when it comes to flash memory, what is it being done is they take few electrons, put it inside a trapped in a floating gate. So that is called a zero state. If there are no electrons inside, it is called a one state. Okay, that's a flash memory for you. Okay, when it comes to optical memory, if we just take a hard disk, they'll take a high power laser and they just drill or groove a small hole which is storing zero. Why it is storing zero? If I incident a light on that groove, the light deflects some other direction, it's not reflected back properly. So in that way, I say there is a zero stored there. If I have a very flat region, high reflective region, it is one for me. Okay, when I incident a light, it is reflected back in some other direction, I receive at some other point. So in that way, a head will realize where the hole is there, where the hole is not there. In that way, a low reflectivity, high reflectivity allows me to store 0 and 1 on a hard disk, like a compact disk. Okay, when it comes to magnetic strip, let's say you take your credit card, behind the credit card black strip is there, you see it is magnetic strip where the electrons inside an atom revolves about a nucleus, you see. So they revolve and they constitute a current. Okay, right, they constitute a current just like a current carrying wire. So let's say electron is moving in a clockwise, current would be in an anti-clockwise. So current would constitute a magnetic field through the axis. You see, magnetic field comes out. That magnetic field is like a dipole, magnetic dipole. So I can arrange all those magnetic dipoles in a particular direction. In that way, I can realize memory whether 0 or 1. If it is all memories, all the magnetic moments of each atom aligned towards the left, I will realize 0. If they are aligned towards the right, so I will so all of them aligned towards the left is 0. If they are aligned toward the right, it is 1. In that way, on a magnetic strip, I can store the information. Okay, so this is how classical memory is being realized more or less these days. Okay, optical memory, yeah, we saw that. When it comes to quantum memory, how it is done? Okay, so as we know, quantum memory is like a quantum hard drive. It can temporarily store a fragile quantum information. Very fragile means sensitive to the around. Okay, without destroying its quantum properties, and then realize it on demand is the one of the requirement. Okay, and this makes them very very crucial to building long distance communication systems and large quantum networks, quantum memory by nature. Okay, so here if you see, let's say there is a quantum memory, I send the qubit information into it, it is stored and it travels and it needs to be read at some point and retrieved at some point. Okay, right? So you keep that in mind. Let's go further and see there are some requirements to be satisfied for any quantum memory to be called a quantum memory or to be used as a quantum memory. So, what are they? Number one, there is something called fidelity. Fidelity is just a cross check. Let's say, for example, I give some money to somebody and I expect that same money to be returned back. Okay, in an intact form, same amount. That is what I give, I return back. The same thing, I create some information in superposition state, which is put onto some qubits. It is traveling some distance, and later on, when I try to retrieve, it should give me the same information, right? So along the way, it lost some information, means it is losing its intactness, its original nature. How much originality is lost? I will just compare and see. Okay, I expect some output intact from the expectation, what is being expected, what is being transmitted, or what is being received. I'll just compare both of them and I will find out what is the fidelity. Very simple. Let's say a quantum state is created, a quantum state is sent. Okay, a quantum state is sent. Along the way, it has become evolved into some quantum E state. I expect to evolve transmitted in the same yes state, but it is evolved into some other state. Now the question is whether they are close. If they are same, you just take an inner product between them. I'll get one. Means 100% they are fine. Whatever I got. But let's say the inner product is less than 100% means I lost some initial like actual information from that. But how much loss? It is expressed in a percentage. In fact, the fidelity is that. If the fidelity is anything less than 100, let's say 95 to 100%, we are fine. If it is less than 100%, 95% or 90%, then a lot of information is being lost. So quantum states are usually represented in terms of block vectors. So the block vector pointing at some direction is sent. It is slightly deviated from that direction is fine. 95% intactness is there, fine. But they all the way they something is sent, they go some other direction. Let's say, let me take some color, different color. Yeah. You see, it is sent in one direction. Along the way it traveled, it changes direction. So I lost some information. So I have here only 75% of the fidelity. So that is very, very important to be known as we do communication in the case of quantum memory based. Okay, right? So we usually expect long coherence time. Okay, means long time. It's like I toss a coin. Flight time, I expect a long flight time. Okay, that is what in the case of quantum memory we expect. So there are technologies being explored starting from qubits, photonics, and so on, trapped ion, and so on, to put the things in long coherence time to do more number of computations on it and have a better computing capability. Okay, so that is to do with the long coherence time. On demand retrieval. So you want to retrieve the information from a qubit, it should not take a long time. There should not be lag. Like say in switches, it's a transistor based switches. When I switch off, when I want to intend to transistor to go on off mode, it takes some time to go to off mode. There is a lag, time lag. So if that lag is there even in a nano and microsecond, but for a computational talks for thousand operations, it becomes a very long time, very long decay. So such things should not be there. So what is expected even in the case of quantum memory, on-demand retrieval is expected. Okay, and efficiency and storage retrieval efficiency close to 100% is required are expected, which if there is any losses that would definitely messes with one of the important property of communication is entanglement distribution rates and scalability in the sense extending the networks to a longer and longer distance to miss scaling up becomes very, very tough if the efficiency is very, very low. Okay, and also multi-mode capacity, ability to store many qubits or multiple photons simultaneously in the same physical memory. Okay, so that enhances data rates in communication. So that is also one of the main requirement in the case of quantum memory. Okay, so the compatibility with the photons, for example, like I said earlier, so stationary qubits are, let's say, atoms or electrons, and flying qubits are photons. Somewhere I mentioned in my notes. Okay, so there should be a, yeah, here there should be a compatibility between stationary qubits to flying qubits, dynamic qubits. So they can should be easily change the exchange information between them. There should be some kind of a coordination between them. If that coordination is not there, I can't have a better quantum memory. Memory retrieval or send encoding and decoding between these things. Okay, right? Okay, so what are the few more requirements? Preservation of entanglement. So yes, Entanglement is a one of the main resource or the recipe for communication in the case of quantum communication. So this memory should allow to preserve the entanglement so that we can extend the communication to a longer distance. That is what is quantum repeaters are, which will be discussed in detail tomorrow, which allows us to do a distributed quantum computing. Means many quantum nodes are there, which are processing units, QPUs. If I have to put them all together and do a very large task, so I need to have a communication happen between them, distributed computing happening between them, which is only possible if I have a quantum memory which allows me to do such thing based on the entanglement. Okay. Right. The scalability and integrability, yeah, in a way, this is our interconnected points. Please, please appreciate what quantum memory should ensure to do a communication. See here, it should be allow us to realize systems that can be scaled and integrated with other quantum technologies like a quantum processors and photonic circuits. Okay, so people are talking about the hybrid quantum computing or quantum communication networks, which may have hardware or photonics, or it may have trapped ion or some other means together, put together like a hybrid manner. So there should be a interconnectivity coordination between them. Okay, so in a way, a practical quantum memory needs to be faithful, efficient, long lived, on demand, and multi-mode and photon compatible, entanglement preserving, and scalable. So this is a final summary of all the requirements that needs to be satisfied or allowed when it comes to quantum memory. Okay, right. So right. So that we got now. So there is a question here: quantum memory capacity, number of W available. W in the sense, I will come to that. I think. Where did I use W? Is there anywhere? Uh, W. Okay. Do we have any quantum networks in India? Or quantum networks widely used in our country, since they seem to be very, very expensive? Okay, now. Okay, quantum memory capacity now. Okay, what is the now available? Okay. So quantum memory right now, up to a few minutes of coherence time, qubits are available. Okay, so we will see. I think there is a chart which is talks about coherence time and so on. Okay, so the ones something like NV center based qubits are very good for a longer coherence time. Photonics ones also very good, but the material based, let's say spin based, they are very very sensitive coherence time lifetime wise. Okay, so another question is quantum networks in India. Yes, there is a quantum networks. So you please check. IIT Madras is a hub which works on quantum communication from the NQM, National Quantum Mission. So Professor Anil Prabhakar, okay, they had a project earlier, Kila. There's a project called Kila. The main objective of the task, the project is to connect the metropolitan cities from Delhi to southern Bangalore and Chennai through optical fiber, where the quantum key distribution is being used to connect them with the absolutely no security issues or no compromise with any tapping with a quantum channel. Such a network is being explored with their initial project. Okay, sorry, initial project was Makan, and later project, right now the next project is Kila. So they're connecting other metropolitan cities also now. In addition to the Macan project, the next upgraded version they're doing. And they're also tackling some things like quantum error correction along the way to ensure that if there is any noise, how to tackle that noise and all those things being explored. So yes, there are quantum networks being explored in India. When it comes to commercial applications, Indian government is thinking about establishing few quantum communication and inspired phones which uses quantum channels to communicate between them so that no third party can tap in. Okay, fine. Please explore Macan and Killa project. It is there on the cloud. Details. Okay, so let's come back to the PPT. Here, if you see performance trade-offs when it comes to quantum memory, what are they? Right? Obviously, there is a plus and minus for any technology when it comes to quantum memory. What are they? The long lifetime, let's say I want to have a long lifetime, obviously lower efficiency. Okay, so we need to balance between them. High fidelity means I have to have the information to be intact as it travels. But the thing is, if I have to do it, I have to enclose the qubit to not to interact with the noise, not to interact with the surrounding. So which means I'm sealing it completely. For having high fidelity, I have to seal the qubit. I have to seal the entire system, not to interact with surrounding. I have to seal so much, even I cannot interact with it later. So there is a high fidelity means that it requires a better isolation. Better isolation means it stops me to interact frequently with this, which means I am confined, my hands are tied. So there should be a balance between how much fidelity I can expect, right? How much fidelity I can compromise. At the same time, I can interact with the system with much ease. So there is a trade-off I have to do. And when it comes to multi-mode storage, if I have to store a lot of things, again, the complexity increases. Complexity in the sense ambiguousness increases as I go to a large number of bed states. Okay, so again, how much I can tackle the complexity, that much multimodal storage I can go. So there is always a balance I have to strike between what is I'm capable, what is the system can offer, at the same time how much I can do. So these are the trade-offs one has to look in. So designing quantum memories involves balancing these conflicting and requirements. Whatever I just told you, we can't expect all of them perfectly satisfying for our given quantum memory. Here and there we compromise and raise some other things depending on my requirement or anybody's requirement. Okay. Like I said, various physical platforms to realize quantum memories. One is atomic ensembles, means I take a collection of atoms where outermost free electrons would constitute a magnetic memory. Okay, so those memories, if you see, at such a quantum level, what happens? The electron, if I just take, which is revolving in a clockwise or anti-clockwise, that itself will become ambiguous, means the corresponding dipole moment for this electron, it can be north south or south north, means it can be upspin or a downspin. That itself would give me a superposition state of alpha upspin, beta downspin, which is a quantum state for me. So this is how atomic ensembles will allow me to realize some qubits. Okay, within the electron orbital spin or electron its own spin. Electron revolves on its own axis, just like Earth rotating on its own axis. Apart from rotating about the sun, it rotates on its own axis. So there is a spin associated with the electron with the orbital spin and its own spin. It is rotating on its own axis. So this is how we can realize the quantum memories at a quantum level. There is something called rare ion doped crystals. So there are rare earth crystals. Within that, I can dope some rare earth ions, and those ions will have a superposition state. From there, I can realize the qubits. We show a little bit briefly about those things in our later slides. Single atoms and single ions possible. Okay, they can be trapped. Okay, so there's something called NV centers. I'll show you figures. What is this NV centers? Or there are silicon vacancies also. You take a carbon, right, diamond. Okay, diamond structure. The carbon have certain structure. You remove few carbons, put a nitrogens inside, and leave few carbons not being replaced by nitrogen. So there is a nitrogen inside, which can be a negative charge, and there is a vacancy of carbon which is a positive charge. Together they create something called a dipole, positive negative dipole. So that is itself a dipole in a various superposition states can exist. From there I can realize a quantum memory. Okay, a photonic memory. inside a cavity. Okay, there is a mirrors. I can send a photon. It can go back and forth. As it goes back and forth, it can have its own quantum information of superposition state, whether it is in a horizontal polarization or it can be a vertical polarization. So that itself could be a superposition state, you see. So a photon can be put in the polarization superposition state. Okay, so there is a most important thing. This is artificial atom, something based on LCR circuits, electronic circuits. Okay, this is very very important because this more or less like 60 to 70% of quantum qubits are based on this artificial atom or a transmons. Okay, so IBM's has transmon based quantum computers, and other companies, most of the other companies. Okay, so this is how quantum memories is being realized. When it comes to atomic ensembles, it's like collective excitation of few atoms. We expect them, all of them behave in the same way, have same behavior, coherence in a sync. But if some of them goes out of coherence, that reduces the lifetime of my superposition state, lifetime of, or the chance of doing computation in longer times. Okay, so there is a quantum optics based technique which is called electromagnetically induced transparency, EIT in short. Based on that, we can realize a quantum memory. There is something called Raman memories. Okay, so this is also based on electron transition states. Using that, we can realize the quantum memory. Okay, so let's quickly understand what is the EIT, electromagnetic induced transparency memory is. When I take a just three level atomic system, let's say one, two, three. Okay, so I can have quantum electronic states transitions in such a way it can happen in a V form. Let's say this is V and this is a ladder. Okay, and the other one is lambda. Okay, so there are two ground states and one excited state, or two ground states and one excited, so on. We can have, this is called a V type configuration, this is a ladder type configuration, this is a lambda type configuration. The question is, same atomic system can be considered in all these three configurations. You know why? I can choose my two incident fields. One is pump field, another is probe field, and their corresponding frequencies. And the strength of the frequencies should be in such a way I have a transitions in so that the V type configuration or ladder type configuration or a lambda type transitions could be realized. Okay, so here, so if I just see, if I want to check how much probe light is being accepted or observed, which is dictated by the coupling field omega c. It's very very interesting. When I don't have a coupling field, let's say coupling field is not there, in that case what happens? I just simply see absorption of a probe field. When the coupling field is switched on, interestingly, the probe field, you see, wherever the probe field, whenever coupling is switched on, probe field absorption is zero, which means omega p is never observed when I have the coupling field very strong. What happens is, whatever electrons are here will be pushed to the level 3. In that way, electrons are not pushed to level 2 because omega c is very very strong. So in that way, we can stop absorption of omega p. Now, how it is being used to realize a memory? Very very interesting thing. Let me remove all these things. Okay, you see, if I have to store the information in level 3 or a level 2, if I have to store the information in level 2, what I do? Somehow I push all the electrons into level 2. Okay, I'll push the electrons to level 2. And the level 2 is electrons are there. And what they do, they may decay to level 1 or level 3. I can stop them decay to level 1. I can put them in level 1. So I can trap them in level 3. So it's called trapping. population trapping. When a population is trapped, no electrons would jump from level 1 to 2. So in that way, I can stop. So this may happen. The information is fed to the system and trapped in the system. Later on, the moment I switch off omega C, that is a coupling field, the information will come back. How many electrons are stored? Those things can come back. This is how the trapping or electromagnetic induced transparency means omega P is transparent for the this kind of atoms. Whenever the coupling field is switched on, the blue color is switched on, okay, in that case I would see, sorry, blue color is coupling is off. In that case, wait a minute, whenever coupling is not there, I'll see a blue color. Whenever is coupling is there, I see a probe field is being not at all observed. That is called a transparency. Okay, so using this technique, we can trap the information within this three level atomic system. Okay, so omega P is a probe field and omega C is a coupling field. It's like two lasers were aligned to same atomic vapor. Okay, right? Rubidium atoms were taken, and for the rubidium atoms, if you send both the lights, let's say coupling field is red color, probe field, let's say green color, if you put them together, interestingly, probe field will never absorb, blue green color will never absorb, it just comes out. The moment I just switch off the coupling field, what happens? Okay, the probe field which is supposed to absorb will not absorb, it just comes out. Whenever coupling is there, probe field will behave as per the coupling field. Okay, right? So now it's a quantum optics, we are not getting into the details and we'll go further. Okay, we have 10 minutes time, so we need to cover a couple more things. So let me quickly jump ahead. Okay, there is rare earth ion based atomic memory. What is that is, we can have rare earth crystal, within that some erbium crystal, we can drop yttrium ions within that. Those ions will have absorption lines in such a way, they will have some peaks, absorption peaks like that. Okay, they may not, like absorption peaks means we only with certain frequencies they will absorb the light. Okay, what I will do now, I'll send in a pulse with the area of the pulse exactly matching with this frequency. This frequency peaks, it is called atomic frequency comb. Atomic frequency comb, which appears like a comb. Okay, now the incident pulse area is exactly matched with frequency peaks. So when I incident such a pulse, what happens? The pulse is absorbed by the frequencies, these atoms in with these frequencies, and they absorb, they retain for some time that energy. After some time, they emit. Okay, so how much delay is there? That delay of returning out is a memory time for me. For example, my input pulse is a blue color pulse, what is shown here. Okay, the which is incident, and the the frequencies whom will absorb the light. Okay, after some time, you see the light, input light comes with a zero output, but there is a echo comes out. It's like when I go and within a very large room, you see, you just shout, your voice will go and hit the walls and wake up back as a reflection, like a echo. Something of that sort happens when it comes to atomic frequency comb. You incident a light with some superposition state information onto it, it goes inside and interacts with this atomic frequency comb or ions, and after some time it retrieved or repelled as an echo. So how much time is there between that? That is my information memory. Okay, so that is enough for us to do a lot of computation. In that way, a quantum computing is possible. In that way, memory is being realized. Okay, so comes back to the most important one is transport, artificial atoms. Okay, what is this is, if you just take a real world atom, let's say natural atom, what is made up of? It has having various orbits about the nucleus. Okay, So 0, 1, 2, and so on. What's interesting thing here is the levels are placed unequally. Let's say 0 and 1, the separation is not equal to 1 and 2. So that is naturally available for a real world atoms. Okay. But, okay, that I can't have, for example, if I have a LCR circuit, LCR oscillator. What is it is? It has an inductor, it has a capacitor. Okay. One minute. I'm sorry. Yeah. It has an inductor, it has a capacitor, okay, and it has some internal resistance. I connect with the oscillatory input field. What happens? It puts the capacitor and the inductor in a quantum states which are represented as a 0 and 1 and 2 and 3. So what are these? Basically, the capacitor and LCR circuit, the nature of the charge on a capacitor oscillate between several states. Let's say corresponding to 0, it may be 5 coulomb, corresponding to 1, it may be 10 coulomb, 15 coulomb, let's say 20 coulomb. So the capacitor state may oscillate between any of these states. What frequency? I can always determine the frequency as square root of 1 by square root of L and C. So I can have a quantum bit states realized using LCR circuit. Only problem here is the states are equally spaced. Whenever I try to create a qubit out of any two states, there is a possibility of those two states information lost to something else, some other two states, because they're equally spaced. It's called linear separation. So I need to bring some non-linearity into it. How to create? People thought, can we replace with a capacitor? Or can I replace inductor with something else? They did try different methods, but what they did interestingly saw is when you replace an inductor with something called superconducting material and the insulator sandwich, it is called Josephson junction, JJ junction. If I replace it, what happens? The non-linearity is introduced between these states. Inductor, so this Josephson junction acts like an inductor, you see. Acts like an inductor. How? When I cool this superconducting material to millikelvin, electrons gets paired up, they form something called Cooper pairs. These Cooper pairs, they don't care the insulator in between. They jump to the other superconducting unit, and they may do oscillations back and forth. And these oscillations may come with some frequencies. It's like an inducing effect with an inductor. So that itself allows to introduce the non-linearity between the states, quantum states. You see, earlier they're equally spaced. The moment you switch on, put in Josephson junction, it becomes unequal states. From there, I can realize a natural real world kind of orbits using LCR circuit with Josephson junction as an inductor. So that is what people being used. This is a IBM chip where there is a superconductor based IBM qubits. They're called transmons. There is a capacitor being realized as a transparent, like as a realized like a plates which are put together, let's say plates. Okay, to increase the lot of area, they will have plates bent in such a way the area of the capacitor is much larger. So that is what you see like say twisted. Okay, twisted, these things uh, are the capacitor plates. Okay, and when it comes to inductor, okay, I'm sorry, when it comes to inductor, okay, when it comes to inductor, they have something called a superconducting material, like some kind of a cantilever. Okay, so some kind of this one. So between one superconductor and the superconductor, there is an insulator. That is how inductor is. This is the inductor part. Okay, right? So that is how artificial atoms are realized. When it comes to envy centers, like I said earlier, nitrogens were used to replace the carbons. That is, create some kind of a dipole which can exist in multiple quantum states. From there, quantum memory is realized. Photonics ones, very simple. There is a photons were sent. There is a beam splitter. Due to beam splitter, photon can go right or left. Okay, how they are going? That is a kind of a beam splitting. It's a kind of a Hadamard gate action. Ion traps, we use electrodes and trap the ions inside, and then we can realize the qubits. Okay, so these are the various ways quantum qubits are realized. So the most important thing is, what is the lifetime, coherence lifetime, when they will decohere. Within each coherence time, how many operations I can realize. You see, for example, let's say electrons, when you take its lifetime is, coherence time is millisecond. Okay, how many operation, like how much time to take, time will take for one operation is 10 to the power of minus 7, means I can realize 10 to the power of 4 oscillation operations on a given second. Okay, it's very very good. When I have, let's say, large number of operations can be realized with ion trap, even though its lifetime is zero point 0.1 second. It allows me to do one operation in just point, sorry, 10 to the power of minus 14 seconds. That's why it allows me a lot of operations, which means usual trend is, or usual tendency for us is, go for a memory which gives me a lot of operations, right? But thing is, trapping, I can't upscale, right? Only few qubits can be trapped, few ions can be trapped. There is a scaling problem there, and controllable problem also there. So due to that, one has to see what is the best for control, what is the best for scaling up. Accordingly, you have to choose what is the better quantum memory and how many operations I can realize. From there, you can do a computing. So there is always a balance should be straight between a coherence time and operation time and number of operations. Okay, right? So this is about quantum memory realization. So let me quickly take one question here. One LCR circuit incorporating Josephson junction takes one atom as a qubit. Yes, you are right. One qubit. Okay, there are four qubits here: Q1, Q2, Q3, Q4, right? So there are, like, yeah. So there is a Josephson junction. This is Josephson junction. Josephson junction, Josephson junction, Josephson junction. Okay, let me remove somewhere else side rod. Okay, right. Fine. So kindly mention some books on quantum memories. Okay. Yeah, for a quantum memories, I don't see a books, but I would be like, recommend you people find, you to just go and find some good journals or review articles. They are very good. I would share one review article which I am using for the presentation. Okay. Yeah, review articles would be very good. Fine. So I'll stop at this point. It is already 5 on a weekend, so not to take any more time. I did answer all the questions along the way, right? Yeah, I will share one quantum memory review article. You can just study that. Fine. Okay. So thank you very much for your attention. Yes, Dr. Venkatramana sir. Okay, so I will hand it over to the organizers. Tomorrow we will meet same time, 3 to 5. I'll talk about quantum repeaters tomorrow. It's like a extension of whatever today we discussed. So far, what is the maximum number of qubits? Yeah. Yeah. See, there is qubits are realized with noise free, right? If they're noisy, then there is a correction need to be done. And then if you are doing a correction, there is something called logical qubits are realized. For realizing one logical qubit, we may consume certain number of noisy qubits. So let's say somebody is claiming that they have 25 qubits quantum system. Out of 25 qubits, how many logical qubits are realized? That is a question. Whenever IBM claims that they have 100 qubit quantum system, means they are talking about 100 logical qubit or a noise free qubits. If they claim 2000 qubits, out of 2000, there may be a lot of them will be noisy. To cover them up, there is a logical qubits needs to be realized. Even 100 logical qubits is very very powerful. 2 to the power of 100 is a data space, memory space. Okay, so it's all in the development stage. Okay, so we can never get disappointed looking at the number of qubits, even at the logical level, because even 2 to the power of 5 is big number for memory processing. Okay, right? So I may not be able to answer directly how many qubits logically is being realized. That's all depends on the people who are working on the field. So let's say IBM, they're as of now few hundreds. They are claiming they are going to reach three digits very very soon. And next to 10 years, they want to go to 10,000. 5 to 10 years, they want to go to 10,000 powerful logical qubits. Okay. As of now, we are in few hundreds range in technology wise. Fine. Okay. So yes, I will stop at this point. Please. Take-
So thank you, Dr. Ashwath. It's a two-way communication lecture is there. So as the participants are consistently interacting with you, so it makes this lecture interesting. So thank you, sir,
Thank
for
you,
the
sir.
lecture. And tomorrow we will have a lecture at the same time, 3 to 5. So
Yes.
all participants are requested 10 minutes before so that you will not have trouble. So thank you, doctor. And
Thank
thank you
you.
all the participants.
Yeah.
This is all for today.
Yeah. Yeah. Good evening, everyone. Bye bye.